Today is Monday, June 26, 2006. We're in Providence, Rhode Island, and we're celebrating the 51st annual meeting of the Health Physics Society. And President Ruth McBurney opened today's session, welcoming everyone to Providence to celebrate 50 fabulous years of the Health Physics Society, and just now beginning our 51st. Shortly after her introductory remarks, we heard from the G. William Morgan lecturer, Dr. Fishoff from Carnegie Mellon University, speaking on the issue of risk analysis and communication. So we see that this issue continues to be of relevance to our profession today. And toward that end, and the lecture as well as the opening remarks, the History Committee continues its efforts to chronicle the pioneers of our society and the charter members of our society and what they did, their contributions to the Health Physics Society. And with me today is one such individual, Mr. Arthur Scott from Toronto, Canada. And I'm Jeff Chapman with the Associated Universities of Oak Ridge. And today we're going to talk to Arthur Scott about his profession, about his life, and his contributions to the society. And Arthur, thank you for spending some time this morning. And if you would, just talk about, if you would, your upbringing in the United Kingdom and what led you to physics, health physics, and then of course to Canada.
Well, thank you very much for inviting me. I was educated in England, and I went to Oxford University to do physics. It had always been my interest, and when I was at Oxford, I saw an advertisement in the laboratory that said they needed a hospital physicist at the local cancer hospital. I thought then, what on earth is a hospital physicist? So I went out to see the fellow, said, well, what's a hospital physicist? He took me around, and it was mainly treatment planning. And at the end of the trip, he said, you're not really interested in this job, are you? Well, I can be a straight man as well as anyone. So I said, well, no, maybe not. So he said, well, very wise. Why don't you write to Professor Rockblatt and give my name, and he runs a training course. So that evening I spoke to my tutor and told him about this, and rather frontally he said, well, if you're interested in that kind of thing, why don't you write to so-and-so and give my name. So I ended up at London University. I was doing a course.
What year was this?
This was in 1963. I was on a course that had been set up in response to the Windscale incident in the UK.
Which was in what year?
57, 58.
So this was, good 5-6 years later.
Yes,
this came to be.
And so it was to provide biology training to physicists, physical training to biologists, all with a general view to a wide-ranging knowledge in the radiation protection field generally. Subsequent to that, I wrote off to a number of research establishments to ask us any chance of the job. And one of the things I wrote to was Atomic Energy Canada Limited in Canada. And they said, well, they didn't have a job at Chalk River, but they were opening a new experimental reactor in Manitoba. And I got a job with them. And I graduated in June, and in August I was in Manitoba.
Interesting. I would like to go back to your time there at the hospital at the University of London.
University of London. I was a joint course with Guy's Hospital and Middlesex Hospital.
So accident dosimetry, accident response, population exposure.
Yes.
What were your contributions at that time to the understanding of the mid-scale accident and its effects on the environment and on people?
Oh, well, the wind-scale accident was hashed over considerably, but not so much in terms of population dose or such things as the questions of organisation. That was the main concern. What had gone right in organising the things, what had gone wrong in organising things. Decisions had to be made relatively rapidly, and all matters had turned out pretty well, but there had been some bad moments, and it was perhaps a rather British kind of thing, but it turned out luckily that there were a couple of people who had some idea of what they were doing and were able to persuade other people.
Right. Well, you see, we live in the world of cell phones, and you heard a cell phone going off, but I think we'll just ignore it. Okay, so once in what year, 65, 66? 65, you moved to Canada.
Yes.
That was a big adventure.
Oh, indeed.
Had you been to Canada before, or
No.
you just boarded the plane and
That's it.
and away you went?
Yeah.
And had you had any colleagues there that you were working with prior?
No, it was
big unknown.
Yeah. My father had been in Canada during the war, so that was the difference.
Oh my. Okay, so you land and then eventually settle in Manitoba,
Yeah.
and then begin to do what specifically?
Well, this was a research reactor, and the main thrust was in materials and fuel testing. So we had hot cells, we had where fuel pieces got cut up. We had a reactor with fuel test loops, material test loops in, and one unique feature of this reactor was it was cooled with organic coolant, HB40, which enabled high temperatures with low pressures. So it was able to look at the higher temperature end of materials under irradiation and things like this. So our main concerns were the general ones of running a research reactor, and much of the work was connected with the hot cells, where there was considerable, you cut up fuel fragments, you get a lot of dust, and it's very hot. And, there were also experiments on fuel fabrication. There were experiments towards reprocessing and plutonium chemistry. So all in all, quite interesting for a new graduate.
Oh, absolutely. Did any of this technology and know-how end up manifesting itself in the Canadian reactor program, the heavy water CANDU reactors?
Yes, a number of. Well, this was all in support of the CANDU program. The reactor was heavy water moderated, but we didn't have much in the way of a tritium problem, because generally the moderator system doesn't require much in the way of maintenance. But yes, we had to take tritium precautions as well when in a few occasions, when pumps needed servicing and so on.
Sure. So that was a couple-year stint for you?
That was a few years subsequent to that. I went to Toronto to join this was still AECL, to join the Power Projects Division, who were responsible for reactor design. And I was with the reactor safety section there. And I was doing calculations of derived release limits, atmospheric dispersion, population dose, that kind of thing. I was also associated with a group that reviewed design implications for radiation exposure. This was the result of one of the AECL demonstration reactors at Douglas Point, where to minimize the infantry of heavy water, the systems had been designed to be very compact. And however, matters were not as well advanced in specification as they are now, and it turned out there were extensive use of cobalt-containing alloys in the system.
I see.
And so cobalt-60 activation products and deposition of the system became a considerable problem. And so it was decided that, well, perhaps we should think of looking at what kind of implications the design has for exposure. In such things as putting long handles on the valves so that ion exchange columns could be valved out from outside the room, rather than having to go in.
Fantastic practices, yes.
Yes. This kind of thing. One of the triumphs was switching the fueling machines from oil lubrication to grease lubrication, because if the oil seals go, you lose the oil pretty quickly, and you have to act very quickly. But with grease lubrication, if the grease seals go, you can wait till the next scheduled shutdown.
Right.
Yes. However, we did so well that they disbanded that section, and I went on to join a consultants in environmental and nuclear things, and for a while there I did atmospheric dispersion, other things with respect to heavy water production plants.
I see. The heavy water production plants, where are they?
We don't have them anymore because the expectation was there would be a large expansion on the CANDO program, and so a number of them were built, and they produced a lot of heavy water, and we have in Sudbury an underground thing that's looking for neutrinos with a huge sphere that's filled with heavy water that nobody is using in a reactor for a moment. So
you have all this experience in, first of all, looking at the wind scale accident and working with the University of London Hospital, and then into reactor safety and design and health physics, and how to reduce exposure to personnel and to the public, and then all your dose modeling type of activities. And somewhere you made the decision to get into radon. Now, how did this come to be, and what was the interesting story there?
Well, what happened was that I don't know if you remember about Grand Junction, Colorado.
I do.
And when the news of this filtered up to the far north, the Atomic Energy Control Board which was sort of a bit like the old USAEC, and had oversight over uranium mining, thought, well, I wonder if anything like that had happened in the Canadian mining towns. And they did a preliminary survey, and they found that there's quite a lot of waste rock around that contained uranium at some economic quantities. And so they thought, well, we need some kind of cleanup program. They put out requests for proposals. The company I was working with put in, and as I was one of the few people who knew what an electron looked like, let alone a gamma ray, we got the contract. So it was anticipated to be largely a earth-moving thing, and I was there to add a air of scientific gloss to it. But they also, by the time the contract had been handed out, they'd also done a radon survey and found that yes, there were quite a lot of houses with elevated radon.
What detector systems did you use at the time?
Well, this was all goosenets, or little air pumps. So I went up and we said, well, of course, bearing in mind Grand Junction experience, which was the radon problems in the houses was caused by tailings around the houses. We said, all right, we'll get in some drills and start to look for the tailings or waste rock. The tailings the mines were considerable distance out of town. So there was no question of use of tailings. Well, the ground there was glacial and large boulders and cobbles. So we had a bit of diversion till we got a hydraulically powered drill mounted on a tractor where we could take soil cores. And we took soil cores and we couldn't find any waste rock. There was waste rock on driveways, which we took off with a front end loader, but it made absolutely no difference at the radon level. Right? So matters were getting a little fraught. So, what's wrong with this picture here? Right. And so taking that we couldn't find any source, and also that we found, because we'd set up a systematic radon survey taking readings in houses several times, the readings were highly variable. And this rather suggested the Grand Junction type of theory that radon was entering the houses by diffusion was incorrect. A, we couldn't find any source, and diffusion implies a fairly constant source. We were seeing values all over the place. So it occurred to me one day after we did an extensive set of measurements in a house, we drilled to the floor slab and took samples out from beneath there and found high radon in the air beneath the floor slab. I said, well, maybe it's this air that's beneath the floor slab is coming into the house. What we have here is a natural radioactive source. The ground around here contains sort of normal amounts of radium, but because it was glacial, there's a lot of gravel, it's relatively porous. But what we're seeing is simply movement of air through the soil into the houses. And so we set around locking up the entry points. My God, it worked.
There you go.
So there we go. Now, by the time this had finished, There was the excitement in Pennsylvania, the Watrous House, the Reading Prom, and I was working for the EPA on radon projects.
So this is in the early 70s?
This is 80s. 85, 86 is the Watrous House. And then, of course, there's a great deal of interest in radon. I mean, we had a meeting, and at the health physics meeting right here, there's sort of only two topics, and that was Chernobyl and radon.
Could you comment at all on your philosophy or your opinion, scientific opinion, on 4 picocuries per liter being the set point for remediation?
Do we have the time?
We have a few minutes. I would really like to know what your feeling is on that. I believe the UK has 32 picocuries per liter, isn't it?
No.
Is that correct? Okay. We go into the Wayback Machine. Okay.
And in Grand Junction, the question was, when is there enough radon around to take action? And what they came up with when they did some surveys, and the figure there was 0.015 working levels above background. And background was 0.005, which comes to 0.02 working levels, 20 milli working levels. So that sets a standard of a kind. In Canada, when we looked at these mining and uranium processing sites, the major one, in fact, was at Port Hope, where there was a radium refinery. And during the demolition of the radium refinery in the 1950s, not all the materials had gone to where they were intended to go. And so there was contamination around town. They did a survey around that time, and they did a similar survey in another town, maybe a few miles down the road, and they came up with, in the uncontaminated town, 99% of the readings in a basement were less than 20 milli working levels. So 0.002 working levels was on a single measurement, was a criterion for remedial action on Port Hope.
I see. 20 milli working levels.
Yes, 0.02. That sort of got moved. They were taking it into account. So that was the action criterion at the other locations as well, 20 milli working levels. And so in a way, if you say the EPA is a bit like Jacob Marley's ghost in how he dragged behind him a chain forged with the deeds of his past. So 20 milli working levels is, well, of course, that's in the old days, 20 milli working levels was 5 picocuries per liter radon.
Aha. I was going to ask you that question. I did not know the relative conversion.
Yes.
Okay.
But when Andy George was working on producing activated charcoal, things for passive measurements. He suggested that a conservative estimate for 20 milli working levels would be 4 picocuries per liter. When you measure the two separately, you come out with an answer. It's around 5, but so it's a conservative thing as well. If we said that 4 picocuries per liter was worth investigating, so the 4 stuck.
Interesting. So it's really from the origin of your work.
Well, it goes back to Grand Junction.
Grand Junction,
yes.
And the Reading Prong, and the Watrous House you mentioned.
Yes, yes. Well, in there they had the levels in many places were so high that the point of these standards was not a question of when you start; it's when you stop, when you reckon you're successful.
So then, what role did all the risk models play in setting? It sounds to me like it had no role. With all the risk models and the lung cancer incidence rate and all of that was more after the fact.
Well, that's
how does that work?
Let's say there must be. I mean, when you do a risk thing, there's elements of judgment, and you can whether the value should be 4 or 5 or 3 is, reasonable men can differ on these matters reasonably, but to some extent the answers are, let's say, predetermined by past actions. You don't want to say, we were wrong. How could we have been so foolish? But just to say on the business of reasonable men can differ. In Canada, after these uranium mining sites had been dealt with, the question arose, well, what should the standard be in general? And the feeling of Health Canada at that time was that 20 picocuries per liter was the level at which you really ought to do something about it soon. Not a question of what was a safe level, but the 20 was an unsafe level. And they, in essence, said, well, until people quit smoking, there's not much point worrying about what's a safe level of radon. And so they defined essentially an unsafe level. Subsequently, with people quitting smoking, we're talking of 20 years ago, that Canada is revising its level down. It will come to, it'll be 200 becquerels per cubic meter.
Now I have one more conversion to do.
Well, the EPA is 148 with spurious accuracy.
Now, you really haven't been active in all of this in the last few years, have you? I mean,
no,
10 years?
When I was when we had an active radon section, when there were a lot of health physics members involved in working in radon research of one kind or other, then yes, I was busy, and I was a president of the radon section at one time.
I see. I was going to ask what your relationship was through the years with the Health Physics Society, and what it meant to you, and how it helped you.
Basically the important thing with the Health Physics Society was that at that time it provided a field where essentially almost all the people who were involved in the radon field could get together and support one another, exchange ideas, and so on. that sense, it was very valuable. Now, of course, the work we were doing for the EPA was to demonstrate that houses could be mitigated. Sort of once the mitigation techniques are established and developed, it's sort of a matter of your local plumbing. Plumbing and radon mitigation, so there's no real need for further research in the sense that we had in those early days, where the business of were there possibilities for prediction. What kind of state legislation might be done. The EPA provided money for state programs. Again, the Health Physics Society was an important venue for people from states to get together and discuss things.
What brings you to the meeting this year in particular? Curiosity?
I like to keep current with things. The environmental radioactivity is an interest for many years. In fact, I first got interested in environmental radioactivity in 1968 when we started to commission our alpha labs, and our alpha air monitors were going off before we had any alpha material in them, and of course this was radon, and so we've been worrying about it since 1968.
Right. Is there anything in particular you'd like to share, an interesting story that you recall, or particularly surprising story beyond the radon, which you've already mentioned?
How many surprises in a lifetime? The radon by soil gas transport rather than diffusion was a major epiphany. On that we had a lot of construction associated with it, and of course we have a horde of construction associated stories, but no interest or membership here. Demonstrating this was so powerful as the power of a poor idea.
We struggle with that daily, I think, today. Okay, well, I think that for me, and I think that for the Health Physics Society and its members in the future, on behalf of them and the History Committee, thank you very much for spending a few moments and reflecting on the past. And what I found particularly fascinating was the radon story in particular, and how you actually worked your way from London to Canada and around again, and reactor safety to the radon issue. I think it's fascinating, so I thank you for that very much.
Yep.
And, okay, thank you.